Alright, so we're going to start with our very first video in this, series of AP Physics C mechanics. I guess what I want to focus on in this one is the very first unit. So we're going to be talking about kinematics, the very first unit. And when I think of the word kinematics, I think of just motion, right? Simple, plain motion. But motion is pretty complicated also at the same time. So we need some way to formalize all the meanings that we have about motion, right? We see cars accelerating. We see a basketball being shot, right? It makes a little parabolic shape. What else do we see? We see people walking. When you're in a car, right, and you see other people driving at your same speed, it kind of looks like they're not moving. So this is what kinematics is all about. We're talking about motion. So that's what I want to first do it as. So here, let me just move this down. There we go. And then let's move it a little bit more. There we go. Yeah, so I want to talk about the definition, kinematics. So I'll start here. So let me zoom in. There we go. Kinematic quantities. That's right here. This is perfect. So here. The very first definition is what is basically what I think of kinematics as. So I'm going to write, usually my definitions will be in red, and I'm going to write the definition in like a pen color, like black, right? When I think of kinematics, I just think of simple, plain motion, right? Things we can observe every day pretty much, more or less. And what I want to do in this one is look at the quantities that describe them, not necessarily relate them all to each other, we'll do that later, but just describe what each term means. So, we also like to talk about, when I talk about objects, I usually like to talk about particles, right? Instead of talking about a human, or like a person, or like a car, I like to talk just about plain particles. And what I think of, we should think of particles as a model. Kind of like a model that simplifies objects, right? I don't want to draw a car in my diagrams. I'd rather draw a particle, like a dot, right? Not everyone's artistic. No one wants to draw a car every single time. They would rather just draw a dot, right? A dot, particle, right? So this is what I'm going to mostly be drawing, a particle or like a box, just something easy to draw. So let's start with our first quantity. So this is our first quantity. We want to talk about position, right? Position, I guess we see this a lot in real life, right? Like I'm here, this is where I am, like on a GPS. You see your position on a map. You can tell your friend, oh, I am here relative to you. How far is that, right? So we need like some sort of reference point. So here, let me just do this. Okay, so a position is, the way I like to think of position is just a location, right? Nothing too difficult about that. Like, it's just a location. However, the thing about position is that we need to have a reference to know where position relative to that, right? Relative to a position, relative to a location. We like to think of position, I like to think of it as like a flag, right? This is like your like a reference point, right? A location relative to a location, this is our reference point, right? And let's say I'm here, right? The particle, I'm here. The position is how far am I here, from here to here, right? Let's say this is 5 meters. Position can also be, I guess you can say, how do you say, position can also be here, right? Right? Anywhere. It can be going here, It doesn't have to be restricted to one line, right? Everything has a different distance from the reference point. And we like to think of that reference point as a coordinate plane, so it's the origin. So the origin is our reference point. So let me just draw here. This is our reference point. 0, right? Usually, here, let me draw this a little. Let me just draw this is the first quadrant. Our reference point here. And then as we move along, the y-axis tracks our position. I'm going to write S for position. And over time, as time passes, how far are we from this, right? So let's say here is 3 meters, and it happens to be at 2 seconds. So at 2 seconds, I am 3 meters away from our reference point, which is 0, right? Kind of like our flag. With this position, we can measure 2 things. So these are the next 2. So we have position. What else do we have? I'm going to put these together. Distance and displacement. These 2 quantities often get mixed up by many people because they're kind of the same thing, but they're actually not. So the way I like to think of this is by drawing this diagram. So let's say I start here, right? I'm here, and I want to take just a walk, I guess, to the park, right? Maybe I have to start walking here, and then I have to take a right turn, take a left turn, and then keep going. Maybe I have to curve here. Let's say the park's right here. So this is where I end, right? This is my start, and this is my end. Not too difficult. What the distance measures is the length of this whole path, right? This whole thing, right? Let's say this was like a segment of 4 meters, 3 meters. This, and then the rest maybe is like this much. That's like 20 meters, right? The distance measures this whole thing. So I traveled, what, 7 plus 20? I traveled 27 meters in distance, right? What the displacement does, it doesn't care how you got to the end. It only matters what are your positions and where did you start, where did you end. So in reality, displacement just likes to measure this line. That's displacement. Right? I don't care that I took a right turn 4 meters out. I just care what's the distance and where did I end and where did I start. What's the distance from where I ended and where I started without looking at the in-betweenness. So that's what I'll write as the definition. So distance is total length of the journey. Displacement, it only cares about where you started and where you ended. The total length of journey, and displacement, oops, I forgot the T, is just where I started, where I finished, and started. Nothing else matters, right? I don't care about taking a left turn here and a right turn there. That's what displacement is. We'll be using displacement more often than distance, just so you know. Alright, the next 2 I want to group together are speed and velocity, right? So, what speed measures? You've seen this when you're driving a car. You see a speed limit sign, right? It's like 60 miles per hour or like 25 in like some residential areas. Parking lot maybe like 5 to 10, something slow, right? That's speed, right? Speed is how fast. So that's what I'll write. Speed, how fast. And what is velocity? Velocity is kind of very similar, but it's also very subtly different. Velocity is how fast and in what direction, right? This what direction makes velocity a vector, right? It makes it a vector. A vector indicates just a size and a direction. So that means speed is a scalar, right? Speed must be a scalar. So I'm gonna scalar. Right? You wouldn't see a velocity limit on the freeway, right? Because then they would have to make sure they know the direction, right? Make sure you're only traveling 60 miles per hour in the north direction, right? But the road curves a lot, so they would have to put a bunch of velocity limits on the road if they wanted to be perfect in the definition. So they're different in the same way. The final quantity is acceleration. This one's a little bit confusing conceptually for many people because they can just plug it into a formula and then they can get the answer, but they don't really know what acceleration really means. I guess the best way to do it is by giving you the definition and looking at an example. Acceleration. How much this velocity is changing, right? Velocity indicates how fast and what direction. So this is also a vector quantity. So now let's look at this example. Let's say I am here in my car. Right? Let's say I'm at rest, so I have a velocity of 0 meters per second initially, so at time 0 seconds. Let's say 1 second later I'm here. So this is, my velocity is, oops, not that, something, and this is at time 1. What I want to know is that because I accelerated so let's say my acceleration points this way, right, we have to be noticeable on our direction. If my acceleration is 2 meters per second squared, what speed am I at 1 second, right? So how much is the velocity changing? The way I like to think of acceleration is not as 2 meters per second squared, but as 2 meters per second every second, right? So it changes 2 meters per second every second. We've passed 1 second, so the acceleration, or the velocity, must change by 2 meters per second. And then maybe here would be time 3, or time 2. Time 2, I still have this acceleration of 2 meters per second squared, or the way I like to think of it, 2 meters per second every second. So I would be at a velocity of 4 meters per second, right? And then the final one would be 6, right? We just keep increasing by 2s. That's the way I like to think of acceleration. So these are the main quantities we'll be looking at, and we already know a lot about time, right? Time just passes every second. It's a scalar quantity, but that's pretty much it, all you have to know about time. And we'll be looking at how we can relate all these various quantities together in the next lesson. So this is it.